A common dietary hypothesis suggests that consuming fermented foods in their raw, natural state is the most effective way to absorb their nutrients. The logic relies on the belief that avoiding heat preserves sensitive vitamins and maintains the viability of active probiotics within the food. Tempeh, a high-density protein block made from fermented soybeans, has become a primary subject of this raw consumption trend. But the physiological reality of the raw soy matrix is significantly more complex than this hypothesis suggests. Because traditional tempeh is often produced in small-scale environments, the unpasteurized fermentation process carries inherent risks of bacterial and fungal contamination. Beyond these safety concerns, moderate thermal processing acts as a required biocatalyst to increase the bioavailability of the nutrients trapped within the soybean. The primary barrier to absorption is a compound naturally present in raw soybeans, phytic acid, or inositol hexaphosphate. Phytic acid operates as a powerful chelator. When it enters the digestive system, it attracts free-floating minerals like iron and zinc. It binds tightly to these essential trace minerals, creating large, stable molecular complexes. These complexes are insoluble in the human gastrointestinal tract. Instead of being absorbed into the bloodstream, they remain bound and pass through the system. Consequently, even if a raw food is rich in minerals, the presence of phytic acid can prevent the body from actually utilizing those nutrients. Thermal kinetics can alter this relationship. Applying heat energy denatures the phytic acid structure, breaking these bonds and releasing the iron and zinc for absorption. This suggests that thermal processing may be a structural requirement to deactivate these antinutrients and increase the total value of the soy matrix. This leads to a critical trade-off. Does the heat necessary to neutralize phytic acid simultaneously destroy the food's macronutrient profile? To test this, researchers published a study in Agritech analyzing how fortification interacts with the cooking process. The study used soy tempeh, specifically fortified with iron and vitamin A, to track nutrient retention under stress. They compared a raw baseline group against a treatment group subjected to moderate thermal processing. The treatment used the traditional bacem method, which involves boiling the tempeh in a mixture of spices and sugar until the liquid is fully absorbed. This statistical analysis provides a clear look at whether boiling destroys the baseline nutritional value of the food. This table summarizes the proximate analysis, comparing the macronutrient concentrations of the raw and cooked states. The bottom row shows p-values of 0 for protein, fat, and carbohydrates, confirming that the boiling process caused a statistically significant shift in the food's composition. Concentrations of protein and fat decreased slightly in the samples that were cooked. This occurs because heat reduces the solubility of certain proteins and causes surface lipids to migrate into the boiling water. Conversely, there was a significant increase in ash and carbohydrates. That carbohydrate jump is an expected result of the preparation method, as the tempeh absorbs palm sugar during the boiling process. While the macronutrient distribution changes, the protein density remains high, suggesting the core nutritional integrity is well maintained. Table 2 shows the performance of the micronutrients, specifically the fortified iron and other trace minerals. For iron, copper, and zinc, the p-values are all above 0.05. These values indicate that there is no statistically significant difference in mineral content between the raw tempeh and the samples that were boiled. This confirms that while heat is required to release these minerals from phytic acid, the thermal energy does not destroy the minerals themselves. The iron recovery rate specifically remained viable at approximately 60 to 65% of the fortified amount. Vitamin A showed a much lower recovery rate of about 25%. However, researchers attributed this to oxidation during the initial mixing of the raw beans, exposure to light and air, rather than the heat of the boiling process. The statistical results demonstrate that the trace minerals survive thermal processing intact, remaining available for absorption even after the transition from raw to cooked states. We can now evaluate these two distinct pathways through the lens of nutrient bioavailability. Path A, consuming the product raw, maintains the risk of bacterial contamination and allows phytic acid to continue chelating essential minerals. The result is a system where the nutrients are present but physically inaccessible to the body. Path B, involving moderate thermal processing, creates a minor shift in macronutrients but preserves the critical micronutrients. By deactivating the phytic acid, this pathway maximizes the bioavailability of the iron and zinc. The minor loss of soluble proteins is an efficient trade-off when compared to the significant gain in mineral absorption. Heat provides a dual solution. It neutralizes microbiological risks while simultaneously deactivating the compounds that block mineral absorption. The empirical data proves that essential minerals like iron and zinc remain structurally stable throughout this process. These biochemical realities are reflected in clinical dietetic guidelines, which favor preparation methods that maximize nutrient uptake. Effective food science relies on targeted processing to ensure that a food's nutrient profile is physiologically functional. Applied thermal kinetics is the mandatory mechanism required to transform the dense soy matrix into a highly bioavailable delivery system.